The nearest star to our Sun is so far away that the fastest object humanity has ever launched would take 73,000 years to reach it. That is not the edge of the galaxy. That is the next house on the street. Your brain already cannot feel that number the way it needs to. Not because you are not trying, because the human mind was shaped by 400,000 years of survival on a single small planet, and nothing in that history ever required it to grasp what a light year means in the body, in the bones, in the gut, the way it grasps a fire or a cliff edge or a storm on the horizon. In January of 2026, NASA confirmed the most distant galaxy ever detected, a galaxy existing just 280 million years after the Big Bang, brighter, more structured, and more chemically complex than anything our models said could exist that early. The model is cracking. 95% of the universe is made of things we have never directly detected and do not understand. 80% of the universe, by volume, is nearly empty. The largest structure we have ever found, a filament of gas and dark matter spanning 3 million light-years, was photographed for the very first time last year. And the tool we use to measure how fast the universe is expanding is now returning two different answers. And the gap between them has crossed the threshold physicists use to declare a discovery. We do not know what the universe is made of. We do not know how big it truly is. And our best model of how it works may be failing. In this video, we will travel from the surface of this planet to the edge of everything light has ever reached, confront the crisis at the heart of modern cosmology, and ask what it means to understand something your mind was never designed to hold. If that sounds like the kind of journey you want to take, please like and subscribe. It helps more than you know. The universe has been here for 13.8 billion years. It has been waiting for something to notice it. Go outside tonight if you can, and find somewhere dark enough that the city has stopped bleeding light into the sky. Wait for your eyes to adjust. Let the shapes resolve, and then look up. On a clear night, far from any artificial light, you will be able to make out somewhere between 4,000 and 5,000 individual stars. They will appear to hang there in every direction, filling the dome of the sky from one horizon to the other. It will feel, as it has felt to every human being who has ever stood in a field and looked up, like you are seeing the universe itself. You are not. Almost every single star you can see with your naked eye tonight is within 1,000 light-years of Earth. That handful of sky, that impression of infinite depth, is a sliver of local space so thin it barely registers against the true scale of what lies beyond it. The Milky Way galaxy is 100,000 light-years across. The stars you can see tonight occupy roughly 1% of that diameter. The Milky Way holds an estimated 200 to 400 billion stars. You can resolve approximately 5,000 of them, roughly 1 in every 50 million. The equivalent of holding up a single grain of sand and claiming you understand the Sahara. The night sky is not a window into the cosmos. It is a porthole into the neighborhood. And here is where the problem becomes more than a matter of scale. The difficulty is not that the universe is large. The difficulty is that the human brain is constitutionally incapable of feeling the difference between 100 light-years and 100 billion light-years. These numbers do not land differently in the body. They produce no physical sensation of greater distance, the way standing at the edge of a cliff produces the sensation of height. They are just bigger words for the same featureless abstract darkness. This is not a personal failing. It is a consequence of how the brain was built and what it was built to do. Human beings evolved in environments where the distances that mattered were measured in meters and kilometers. 400,000 years of selective pressure shaped the human mind into an extraordinarily efficient navigational tool for a planet 12,742 kilometers in diameter, and left it with essentially no capacity to intuitively process anything larger. The architecture of the brain simply does not have a register for a light year. A light year is the distance light travels in a single year. Light moves at just under 300,000 kilometers per second. In 1 year, it covers approximately 9.5 trillion kilometers. That is the unit we are using when we say the nearest star is 4.24 light-years away. That is the unit we are using when we say the observable universe extends 46 billion light-years in every direction. You can read those numbers, you can do the arithmetic, but you cannot feel them, because nothing in your evolutionary history required you to. What you can do, what this video is going to ask of you, is follow the scale one step at a time. Not to arrive at a feeling that is impossible to arrive at, but to trace the outline of the thing clearly enough that its shape lands, even if the full weight of it never quite does. So, here is where you are. You are on a planet orbiting an ordinary middle-aged star, sitting inside a local bubble of hot, low-density gas, roughly 1,000 light-years across. A cavity inflated by supernova explosions over the past 10 to 20 million years. The European Space Agency's Gaia satellite completed the first full three-dimensional map of that bubble in 2022. Its boundary is lined with young star-forming regions, new stars igniting along the shell of an ancient explosion. 1,000 light-years. The immediate vicinity. Inside a galaxy 100,000 light-years across. Inside a universe that extends tens of billions of light-years beyond the galaxy in every direction. And you cannot see any of it from where you stand. You are inside a structure so large that a view of it from the outside is physically impossible. Everything you can see tonight is the inside surface of a sphere roughly 1,000 light-years in radius, with you at the center. The rest of the galaxy, the other 99% of it, the hundreds of billions of stars you cannot see, the supermassive black hole at the galactic core holding everything in a slow gravitational spiral, is hidden behind gas, dust, and sheer distance. The universe is vast. You already knew that. But the size is not the most important thing here. The most important thing is that you are already inside it, already embedded in structures you cannot see, already looking at a sky that is showing you almost nothing of what is actually there. The moon looks reachable. On a clear night, you can see texture on its surface with the naked eye, the dark plains, the pale highlands, the suggestion of craters at the disk's edge. It has a quality no other object in the night sky possesses, the quality of being a place rather than a point of light. The moon is 384,400 kilometers from Earth. At escape velocity, the journey takes approximately 3 days. The Apollo astronauts spent 72 hours crossing that distance in a spacecraft roughly the size of a large caravan. 12 human beings have stood on its surface. Every one of them took 3 days to get there. 3 days. To the nearest thing to us in the solar system. Hold that. Because the next number is going to move the reference point entirely. Mars sits, at its closest approach, approximately 54.5 million kilometers away, 142 times farther than the Moon. The light speed delay between Earth and Mars ranges from 3 minutes to 22 minutes, one way. Every command NASA sends to the Perseverance rover, currently gathering rock samples in the Jezero crater, travels for up to 22 minutes before it arrives. Then the mission team waits another 22 minutes to hear whether the command was received. Real-time conversation is not difficult. It is impossible. The physics of distance and the absolute speed limit of light make it so, regardless of how good the technology becomes. In 2014, the Curiosity rover pointed its cameras upward and photographed Earth from the Martian surface. Our planet appeared as a pale bluish point of light, barely distinguishable from the surrounding stars. Everything you have ever known, every city, every ocean, every person alive, and every person who has ever lived, compressed into a single pixel in a Martian sky. And that photograph was taken from 63 light seconds away, less than 1/10,000th of the distance to the nearest star. Neptune, the outermost recognized planet, orbits the Sun at roughly 4.5 billion kilometers, 30 times the Earth-Sun distance. Voyager 2 made its flyby there in 1989 after 12 years of travel. A signal from Neptune reaches Earth in approximately 4 hours. 4 hours at the speed of light, to reach the outer edge of the planetary solar system. And the planetary solar system is itself a fraction of the Sun's full gravitational domain. Beyond Neptune lies the Kuiper Belt, a ring of icy objects extending to around 50 astronomical units. Beyond that stretches the Oort cloud, a diffuse shell of comets and debris reaching perhaps 100,000 astronomical units from the Sun. The outer edge of that cloud marks the rough boundary of the space our star gravitationally holds, and that boundary lies approximately 1.5 to 2 light-years from Earth. The nearest star is 4.24 light-years away. Think about that for a moment. The gap between our solar system and the next stellar system is larger than our entire solar neighborhood. The space between houses is bigger than the houses themselves. Voyager 1, the fastest object humanity has ever built, has been traveling for nearly 50 years at 61,000 kilometers per hour. It currently sits approximately 24 billion kilometers from Earth. A genuine, extraordinary achievement, the product of physics and engineering and decades of human effort. Bolted to its side is a gold-plated copper disc, the Voyager Golden Record, assembled by a committee chaired by Carl Sagan, containing greetings in 55 languages, 90 minutes of music, and the sounds of a living world, wind, rain, a mother, and her newborn child. It was designed to be found. The odds that it will ever be found are, in any honest assessment, essentially zero. Space is too large. The distances are too great. It will drift through interstellar space for billions of years, outlasting every building and every civilization on Earth, almost certainly unheard. It is also less than 1% of the distance to the nearest star. Less than 1%. After nearly 50 years of uninterrupted flight. That is where the scale stops being an impressive number and starts becoming something harder to name. Something immense and patient and entirely indifferent to how far we have come. The nearest star is right there, in terms of the galaxy. It is practically next door, and at our fastest speed, with our best technology, launched decades ago and still going, we have covered less than 1% of the journey. The galaxy has 200 billion more stars beyond it. And beyond the galaxy, the mind goes quiet here because language starts to fail. The observable universe contains an estimated 2 trillion galaxies more. We are just getting started. There is a common assumption about Voyager 1 that is worth examining carefully because it illustrates something important about how we think about the solar system versus how the solar system actually is. Most people, when they hear that Voyager crossed the heliopause in 2012, the boundary where the solar wind gives way to the interstellar medium, assume that means it left the solar system. It did not. The heliopause marks the edge of the Sun's magnetic bubble. It does not mark the edge of the Sun's gravitational reach. Those are two very different things, and the distance between them is staggering. Beyond the planets, beyond Neptune, beyond the Kuiper Belt with its rings of ice and rock, there is a structure called the Oort cloud. It is not a disk, it is a sphere, a vast, diffuse shell of comets and frozen debris that surrounds the solar system in every direction. It begins at roughly 2,000 astronomical units from the Sun and extends outward to perhaps 100,000 astronomical units. An astronomical unit is the distance from Earth to the Sun, 150 million kilometers. The outer edge of the Oort cloud is therefore somewhere in the region of 15 trillion kilometers away. Voyager 1 is currently at approximately 165 astronomical units. The inner edge of the Oort cloud begins at 2,000. At its current speed, Voyager will not reach the inner boundary of the Oort cloud for another 300 years. It will not clear the outer edge, will not truly exit the Sun's gravitational neighborhood for approximately 30,000 years. 30,000 years. Let that number sit. 30,000 years is longer than all of recorded human history. The first permanent cities appeared in Mesopotamia roughly 5,000 years ago. The pyramids at Giza were built roughly 4,500 years ago. The entire written record of human civilization, every empire, every language, every scientific discovery, every war, every work of art, fits inside 5,000 years. Voyager needs 30,000 years just to reach the edge of our own stellar neighborhood. not to reach another star, not to cross the gap between solar systems, just to exit the sun's domain. And then the real crossing begins. Proxima Centauri, the nearest known star to our sun, is 4.24 light-years away. At Voyager, one's current speed of 61,000 kilometers per hour, reaching it would take approximately 73,000 years. Voyager is not even heading in that direction, but the number is what matters. 73,000 years, at our fastest speed, for the closest possible destination. Now consider what we have actually sent into that void. The Golden Record, that gold-plated copper disc bolted to Voyager's side, carries 115 images encoded as audio signals, greetings spoken in 55 human languages, and 90 minutes of music. Bach, Beethoven, Chuck Berry, a Navajo night chant, a Pygmy girl's initiation song, an Azerbaijani folk melody. There are sounds of earth, surf, wind, thunder, the songs of birds and whales, the sound of a mother kissing her child for the first time. It was assembled by a committee chaired by Carl Sagan, who understood precisely what he was doing, sending a message not to any specific recipient, but into an indifferent void, on the vanishingly small chance that something capable of understanding it might one day find it. The probability of that happening is, in any rigorous honest accounting, effectively zero. The volume of interstellar space is so incomprehensibly large, and Voyager's trajectory so specific, that it will pass within 2 light-years of another star only once in the next 40,000 years, and even then, nothing is known to inhabit it. The record will almost certainly drift forever, unplayed, in the dark between stars. It is the most remote physical object humanity has ever made. It is also, in a certain light, the loneliest. But there is something else we have sent into space, something faster than any spacecraft, and launched not from a launch pad, but from every radio tower and television transmitter and radar installation on Earth for the past century. Electromagnetic radiation, radio waves, television signals, military communications, travels at the speed of light. Since the early 20th century, this halo of human noise has been expanding outward from Earth in an ever-growing sphere, currently approximately 125 light-years in radius. 125 light-years. That sounds like a meaningful distance. In a galaxy 100,000 light-years across, it is not. If you placed a map of the Milky Way on a standard football pitch, our entire radiosphere would be a dot the size of a pinhead, somewhere near the halfway line. Every television broadcast ever transmitted, every radio program ever aired, every military radar pulse, all of it contained within a bubble that the galaxy would not notice if it vanished tomorrow. There are an estimated 200 to 400 billion stars in the Milky Way. Our radiosphere has reached the neighborhood of a few thousand of them. If anyone is out there, and if they are listening on the right frequencies at the right time, and if they happen to be within 125 light-years of us, they might, in principle, have detected us. Beyond that distance, we are invisible. We have been broadcasting our existence for a century, and the vast majority of our own galaxy has had no opportunity to hear us. This is where the scale becomes personal. This is where it stops being a feature of the cosmos and starts being a feature of what we are, and where we are, and how alone we might actually be. The Milky Way is a barred spiral galaxy. That sounds like a classification, a label applied from outside. But it is a shape, and the shape matters. Imagine a lens of stars, roughly 100,000 light-years in diameter and about 1,000 light-years thick at the disk. At the center, a dense bulge of older stars surrounding a bar-shaped structure of gas and star clusters. From that central bar, 2 major spiral arms, the Scutum Centaurus arm and the Perseus arm, sweep outward in graceful arcs, along with several smaller arms and spurs. The whole structure rotates slowly over hundreds of millions of years. You live in one of the smaller structures. The Orion arm, sometimes called the Orion spur, is a minor spiral feature connecting the larger arms, and the Sun sits within it at a distance of approximately 26,000 light-years from the galactic center. We are not at the core. We are not at the edge. We are in an unremarkable stretch of a minor spur, in an unremarkable part of an ordinary galaxy. And in every direction that we look, the stars extend far beyond what any instrument we have ever built can fully resolve. The galactic center is a different world entirely. The density of stars near the core is orders of magnitude greater than in our neighborhood. The region is threaded with intense magnetic fields, swept by powerful stellar winds, and lit by the deaths of massive stars that burn through their fuel in millions of years rather than billions. And at its absolute heart sits Sagittarius A star, a supermassive black hole with a mass of approximately 4 million times that of the Sun. For decades, Sagittarius A star was inferred rather than observed. Its gravitational influence on the stars orbiting near the galactic center was tracked over years, then decades, by teams including those led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics and Andrea Ghez at the University of California, Los Angeles, work that earned them the Nobel Prize in Physics in 2020. The stars near the galactic center moved in ways that required something extraordinarily massive and compact at the origin point of their orbits. There was no reasonable alternative to a black hole. Then, in 2022, the Event Horizon Telescope collaboration published the first direct image of it. The same global network of radio telescopes that had already imaged the black hole at the center of the galaxy, Messier 87, now turned to our own galactic center and resolved, for the first time in human history, the glowing ring of superheated material surrounding the darkness at the Milky Way's core. It is there. It has always been there. We just needed the instruments large enough to see it. The Sun orbits this center at approximately 220 kilometers per second. That is fast, far faster than any human intuition registers. Yet at this speed, one complete orbit of the galaxy takes between 225 and 250 million years. Astronomers sometimes call this a cosmic year or a galactic year. The last time the Sun completed a full orbit and returned to approximately its current position in the galaxy, the Triassic period was just beginning on Earth. The first dinosaurs had not yet appeared. The last time before that, the Permian extinction had only recently ended. The galaxy turns on timescales that make the entirety of complex life on Earth fit within a single lap, and the galaxy itself is not empty between the stars. The space between them is threaded with what astronomers call the interstellar medium, a diffuse mixture of gas and dust that fills roughly 99% of the volume of the Milky Way by mass. Most of it is hydrogen. Some is molecular, forming dense cold clouds where new stars are born. Some is atomic, drifting in the relative warmth between spiral arms. Some is ionized, heated to tens of thousands of degrees by the radiation of nearby stars. The interstellar medium is not nothing. It is the raw material from which every star, every planet, and every molecule that has ever been part of a living thing was ultimately assembled. The atoms in your body passed through the interstellar medium before they found their way into a solar system, before they became part of a planet, before they became part of you. Here is a way to hold the scale of the galaxy before we step outside it. If the Milky Way were shrunk to the size of the continental United States, the Sun would be an object far too small to see with the naked eye, sitting somewhere in the state of Kansas. Proxima Centauri would be roughly 6 kilometers away. The galactic center would be in Los Angeles. And the entire local bubble, the 1,000 light-year cavity the Sun has been drifting through for millions of years, would be a region roughly the size of a large city. That is the galaxy. 100,000 light-years of stars, gas, dark matter, and deep time, with the Sun somewhere in the middle distances, unremarkable, uncentral, and utterly ordinary in every way that matters for what is about to come next. For most of human history, the Milky Way was the universe, not a metaphor, not an approximation. The literal totality of everything that existed. When ancient astronomers looked at those faint smeared patches of light scattered across the sky, the ones that looked like clouds of gas caught between the stars, the assumption was straightforward. They were clouds of gas caught between the stars, objects within our galaxy, part of the furniture. The universe was one island of light in an infinite surrounding darkness, and that island was ours. The assumption held through centuries of increasingly sophisticated observation. Even as telescopes grew larger and more powerful through the 17th, 18th, and 19th centuries, the question of whether those fuzzy patches, the spiral nebulae, as they came to be called, were inside the Milky Way or outside, it remained genuinely unresolved. The instruments were not yet good enough. The distances were too great for the methods available. By 1920, the debate had crystallized into two serious scientific positions, and in April of that year, the Smithsonian Institution in Washington hosted a formal discussion, later called the Great Debate, between two of the leading astronomers of the era. Harlow Shapley argued that the Milky Way was enormous, far larger than previously thought, and that the spiral nebulae were small objects contained within it. Shapley had done important work locating the Sun's position relative to the galactic center, correctly identifying that we were not at the middle of the galaxy, but far out toward one edge. He was right about that, but he was wrong about the nebulae. Heber Curtis of the Lick Observatory in California took the opposing view. He argued that the spiral nebulae were too large, too structured, and too numerous to be gas clouds within the Milky Way. They were, he contended, separate galaxies in their own right, island universes, each comparable to the Milky Way itself, each separated from us by distances far beyond anything the telescopes of the time could directly measure. He was right, but neither man could prove it. The proof came 4 years later, and it came from a man working in the dark. Edwin Hubble was using the 100-inch Hooker telescope at Mount Wilson Observatory in California, the largest telescope in the world at the time, to systematically photograph the Andromeda Nebula, that soft smudge of light visible to the naked eye in the autumn sky. In 1924, examining his photographic plates, he identified something crucial, a Cepheid variable star, then another, then more. Cepheid variables are stars that pulsate. They brighten and dim in a regular cycle, and the period of that cycle is directly related to their intrinsic luminosity. A Cepheid that completes a cycle in 30 days is genuinely brighter than one that cycles in 10 days by a predictable and calculable amount. This relationship, the period luminosity relationship, had been established by Henrietta Swan Leavitt at Harvard College Observatory more than a decade earlier, through painstaking analysis of thousands of variable stars in the Magellanic Clouds. Leavitt's discovery was one of the most consequential measurements in the history of astronomy. It gave astronomers a ruler, a way to calculate true distances to objects that were otherwise unreachably far away. Hubble used that ruler. By measuring the period of the Cepheids he found in the Andromeda Nebula, he calculated their intrinsic brightness. By comparing that to how bright they appeared from Earth, he calculated the distance. The number he arrived at was approximately 900,000 light-years, far beyond any conceivable boundary of the Milky Way. Later measurements revised this figure upward to approximately 2.5 million light-years, but even the first estimate was enough to settle the matter definitively. Andromeda was not a gas cloud inside our galaxy. It was a separate galaxy, an island universe, as Curtis had argued. The debate was over. The conceptual earthquake that followed is difficult to overstate. In a single set of measurements, the known universe expanded by orders of magnitude. The Milky Way, which generations of astronomers had understood as the totality of existence, became one galaxy among what would turn out to be an almost incomprehensible number of others. The night sky was not the universe. It was a view from inside one galaxy, one of billions. Andromeda sits 2.5 million light-years away and contains approximately 1 trillion stars, roughly twice the stellar population of the Milky Way. It is the most distant object visible to the naked eye under good dark sky conditions. A smudge of ancient light that has been traveling toward your eye for 2.5 million years, leaving Andromeda before our ancestors were fully human. And it is also, though this takes some time to absorb, heading toward us. The Milky Way and Andromeda are on a gravitational collision course, expected to begin their merger in roughly 4.5 billion years. Not a violent collision of solid objects. Galaxies are mostly empty space, but a slow, gravitational dance that will over hundreds of millions of years reshape both into something new. The galaxy count has expanded dramatically since Hubble's day. The Hubble Space Telescope, pointed at a seemingly empty patch of sky in 1995, resolved hundreds of galaxies in a region so small it would be covered by a grain of sand held at arm's length. Then thousands. Deeper images revealed more. The current best estimate places the number of galaxies in the observable universe at approximately 2 trillion. And that number is itself almost certainly an undercount, because the most distant and faintest galaxies remain below the detection threshold of any instrument yet built. 2 trillion galaxies, each containing billions to hundreds of billions of stars, each separated from its neighbors by distances measured in millions of light years. The Milky Way is one of them. Here is what 2 trillion galaxies actually look like at the scale of the universe. They are not scattered randomly. They are not distributed uniformly through space like raisins in a cake, each equally spaced from the next. The universe has structure, deep, architectural structure, and that structure operates on scales so vast that individual galaxies are the smallest meaningful unit of it. At the very largest scales, matter in the universe is organized into what cosmologists call the cosmic web, a three-dimensional network of filaments, sheets, and nodes separated by enormous near-empty regions called voids. The filaments are the strands of the web, elongated concentrations of dark matter, gas, and galaxies stretching hundreds of millions of light years. The nodes are the intersections where filaments meet, and it is at these nodes that the largest gravitationally bound structures in the universe are found, galaxy clusters and superclusters containing hundreds or thousands of galaxies each. The voids are the vast spaces between, regions of dramatically below-average density that together account for roughly 80% of the observable universe's volume. The cosmic web is not a recent theoretical invention. Its conceptual foundations, built through observational work across the 1980s and 90s, as redshift surveys began revealing that galaxies were not randomly distributed but traced large-scale patterns. The CFA Redshift Survey, led by Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics, produced in 1989 one of the first maps clear enough to show the pattern unmistakably. Their data revealed a vast sheet of galaxies stretching across the survey region, a structure they called the Great Wall, hundreds of millions of light years long, and the voids on either side of it. The web was real. It was in the data. The term itself was formalized by the cosmologist Richard Bond at the Canadian Institute for Theoretical Astrophysics in 1996. And it has been the standard framework for understanding cosmic large-scale structure ever since. The question of what produces the web leads immediately to one of the most important and least understood features of the universe. But before we get there, it is worth understanding how the web was built in the first place, because the answer reaches back to the very first moments after the Big Bang. The universe began almost perfectly uniform. Almost, not perfectly. Quantum mechanics, the physics governing behavior at subatomic scales, ensured that the density of matter and energy in the earliest universe was not exactly the same everywhere. There were tiny fluctuations, variations in density of roughly 1 part in 100,000. Regions that were infinitesimally denser than average. Regions that were infinitesimally less dense. At the moment those fluctuations were imprinted, they were so small as to be barely measurable even with our most precise instruments today. But gravity is patient. Over hundreds of millions of years, then billions of years, gravity amplified those microscopic differences. The slightly denser regions attracted more matter. The slightly emptier regions lost matter to their denser neighbors. The differences grew. The rich got richer. The empty got emptier. The slight wrinkle became a ridge. The ridge became a filament. The filament became the web. This process is extraordinarily well understood theoretically and has been reproduced in supercomputer simulations with remarkable accuracy. The Millennium Simulation, developed by Volker Springel and colleagues at the Max Planck Institute for Astrophysics in 2005, modeled the evolution of the web at sufficient resolution to compare directly with observed galaxy distributions. The match was striking. The simulated universe produced the same filaments, nodes, and voids seen in the actual sky. The web emerged naturally from the initial conditions of the Big Bang, driven by gravity acting on quantum noise over billions of years. There is something important about what drives the web's structure at its deepest level. Ordinary matter, the atoms, molecules, gas, and stars that make up everything visible, is not the primary ingredient. It is a passenger. The dominant gravitational force that shaped the web is a form of matter that emits no light, absorbs no light, and has never been directly detected. It is invisible, and it makes up approximately 85% of all matter in the universe. The cosmic web is built from darkness. The galaxies we see, the 2 trillion islands of light spread across the observable universe, are not the web itself. They are what collected inside it. They formed in the gravitational wells the invisible scaffolding created, clustering at the nodes where filaments intersect, strung along the strands in between. Remove the invisible component from the models, and the web does not form. The filaments, it turns out, are not static. They are not merely the framework on which galaxies hang. They are active supply lines, channels through which gas flows continuously from the underdense voids toward the dense nodes, feeding the galaxy clusters that sit at the intersections. The web is not a finished structure. It is a process, still unfolding, still drawing matter from the emptiness and concentrating it at the crossroads. The universe, at its largest scale, is a living machine, and we are somewhere inside it, on a strand, far from any intersection, looking outward into a structure whose full extent we are only now beginning to understand. For nearly 40 years, the cosmic web existed in 2 places: in the data, in the galaxy surveys, the redshift maps, the careful cataloguing of how matter is distributed across the sky, and in the simulations, in the supercomputer models that began from the initial conditions of the Big Bang and evolved forward in time, producing a universe that, when plotted, looked unmistakably like a web of glowing threads. What it did not exist in was an image. No one had ever directly photographed a filament. This was not for lack of trying. The filaments of the cosmic web are made primarily of dark matter, which by definition cannot be seen, and of diffuse hydrogen gas, which in principle can emit a faint glow. But the density of that gas is extraordinarily low, spread across millions of light years, far thinner than the best vacuum achievable in any laboratory on Earth. The glow it produces is so dim that it falls below the detection threshold of almost any instrument ever built. Mapping the web from galaxy distributions is like inferring the shape of a river from the positions of the boats on it. You can understand the general structure, but you have never seen the water. The challenge required an instrument capable of something unusual, collecting a spectrum, a full breakdown of light by wavelength, for every single pixel in its field of view simultaneously. Most telescopes, when they take a spectrum, point at one object and analyze the light from that single source. To find a filament, you need to analyze the light from an entire region of sky at once, hunting through thousands of pixels for the specific signature of hydrogen emission at the precise redshift of the structure you are looking for. This is technically formidable. The instrument that made it possible is called MUSE, the Multi-Unit Spectroscopic Explorer. It sits on Unit Telescope 4 of the European Southern Observatory's Very Large Telescope at the Paranal Observatory in Chile, one of the highest and driest sites on Earth, where the atmosphere is thin enough and stable enough to make precision observations of this kind feasible. MUSE does not take a photograph in the ordinary sense. It takes a data cube, a 3-dimensional block of information in which every position on the sky has its own complete spectrum. From that data cube, researchers can extract the faint signal of hydrogen gas at any redshift they choose, separating it from the background noise of everything else in the field. In 2025, a team led by Davide Torralba Torregrossa at the University of Milano Bicocca, working in collaboration with researchers at the Max Planck Institute for Astrophysics, used MUSE to target a specific region of sky containing a cosmic Webb filament at redshift 3. This means the light they were observing left its source when the universe was approximately 2 billion years old, roughly 14% of its current age. The filament connects two galaxies, each hosting an active supermassive black hole at its center. Those black holes act as luminous beacons, illuminating the surrounding gas and making it easier to detect. The team pointed MUSE at this region and left it there for more than 150 hours. 150 hours of observation time on one of the most powerful optical telescopes on Earth, focused on a single patch of sky, accumulating photon by photon, the faint trace of hydrogen emission in a 3 million light-year bridge of gas between two ancient galaxies. The Atacama Plateau, where the Very Large Telescope sits, receives fewer than 2 weeks of rainfall per year. The nights are long and dark and extraordinarily clear. Even so, 150 hours represents a commitment of telescope time that few projects achieve. The image that emerged from that data is unlike most images in astronomy. It does not show bright objects against a dark background. It shows something softer, a diffuse glowing structure, faint and extended, connecting two compact bright sources. The filament appears as a luminous bridge, its gas tracing a path through intergalactic space, marking the route along which matter flows between the two galaxies. At its widest point, the filament is roughly 3 million light-years across, 30 times the diameter of the Milky Way. The team could identify, within the image, exactly where the gas belonging to each galaxy ended and where the gas of the filament itself began. That boundary had never been observed before, not once in human history. When Torralba Torregrossa and the team overlaid their observations on cosmological simulations produced by the Max Planck Institute, the agreement was precise. The shape of the observed filament, its density profile, the brightness distribution of the hydrogen emission, all of it matched the simulation predictions with a fidelity that confirmed decades of theoretical work in a single image. The Webb is real. It looks exactly as the models said it would. We have a photograph to prove it. That same year, a separate team at Oxford University published a discovery that added another dimension to the picture. Using data from MeerKAT, the South African radio telescope array that represents one of the most sensitive instruments of its kind, they identified a chain of 14 galaxies embedded in a cosmic filament 5.5 million light-years long. All 14 galaxies are spinning in the same direction. The entire structure, a filament spanning millions of light-years, is rotating as a coherent unit. This was unexpected. Filaments were understood as passive structures through which matter flows, not as objects with their own angular momentum. The discovery suggests that filaments actively transfer rotation, that the Webb itself spins, that the motion of matter within it is not just directed inward toward the nodes, but involves a rotational energy that propagates across cosmic scales and is ultimately imparted to the galaxies embedded within it. The Webb is not scaffolding. It is not a passive container for galaxies. It is dynamic, rotating, flowing, and feeding. A structure that has been shaping the galaxies within it since long before any instrument existed that could see it. Now, at last, we can. When you look at the cosmic Webb, in the simulations, in the maps produced by Galaxy Surveys, and now in the first direct photographs, something else becomes clear beyond the filaments and the nodes and the galaxy clusters at their intersections. Most of it is empty, not sparsely populated, not thinly scattered. Genuinely, profoundly, almost completely empty. The voids that sit between the filaments of the Webb account for roughly 80% of the observable universe by volume. The filaments and sheets and nodes, all the structure, all the galaxies, all the matter that has ever been observed by any instrument, occupy the remaining 20%. The universe is not a place that happens to have some empty regions between the interesting parts. The universe is mostly empty, and the interesting parts are an exception. This is not an impression produced by limited observation. It is a confirmed feature of how matter is distributed at the largest scales, and the voids are among the best characterized structures in cosmology. In 1981, a team at the Harvard-Smithsonian Center for Astrophysics was conducting a routine survey, measuring the distances to galaxies in a region near the constellation Boötes by observing their redshifts. It was systematic work, the kind that had been building the first three-dimensional maps of the galaxy distribution. Robert Kirshner, leading the survey along with his colleagues, expected to find galaxies distributed roughly as they were elsewhere in the sky. What he found instead was a gap in the galaxy distribution so large, so complete, and so symmetrical that at first the team assumed something had gone wrong. They checked their data. They checked their instruments. The gap was real. What Kirshner and his team had found was the Boötes void, a roughly spherical region of space approximately 330 million light-years across. In a volume of that size, a normal region of the universe would contain roughly 2,000 galaxies. The Boötes void contains approximately 60, strung along a thin filamentary thread that runs through its center, surrounded on every side by an emptiness that extends for hundreds of millions of light-years. You could take 3,000 Milky Way galaxies, line them up edge to edge across the void's full diameter, and they would still not fill it. Greg Aldering, an astronomer at the Lawrence Berkeley National Laboratory, once offered a thought experiment that captures what it would mean to live inside such a void. If the Milky Way had formed at the center of the Boötes void instead of where it did, the night sky would look the same as it does to us, full of stars, full of the familiar constellations. But beyond those local stars, beyond the Milky Way's own boundaries, there would be nothing visible to even the most powerful telescopes of the early 20th century. No Andromeda Nebula to resolve into a separate galaxy. No spiral nebulae at the edges of the sky to argue about. The Great Debate of 1920 would not have been a debate at all, because Curtis would have had no evidence for the island universe hypothesis. An entire civilization, armed with all of our early cosmological tools, would have concluded with complete confidence that they were alone, that the Milky Way was the universe. And they would have been wrong, with no means of knowing it. The Boötes void is not unusual. It is large, one of the largest known voids, but not exceptional in kind. The universe is laced with them, in all directions, at all distances. What produces them is the same process that produced everything else we have discussed. The quantum density fluctuations imprinted in the earliest moments after the Big Bang were not just slightly above average in some places and slightly below in others. The below-average regions were the seeds of the voids. As gravity amplified the fluctuations over billions of years, pulling matter toward the denser regions, the less dense regions were progressively emptied. Matter drained out of them and into the filaments and sheets around their edges. The slight deficit became a significant deficit. The significant deficit became an enormous near-total emptiness. The voids did not form by having matter removed from them. They formed because the matter that was in them was pulled away. This means voids are not static features of the universe. They are growing, slowly but continuously, as matter at their edges continues to drain outward toward the surrounding structure. They are the universe's exhale, a process that began with the first density fluctuations and has not yet finished. Now consider where the Milky Way sits within all of this. In 2013, Ryan Keenan, Amy Barger, and Lennox Cowie at the University of Hawaii published a detailed analysis of the galaxy distribution in our local region of the universe. What they found was that the Milky Way does not sit in a typical part of the cosmic web. It sits inside a void, a large one. The structure is called the KBC void, named for the initials of the three researchers, or sometimes the local hole. It is a region of significantly below average galaxy density, roughly 2 billion light-years across. Galaxy counts within this region are estimated to be somewhere between 15 and 50% lower than the cosmic average. The Milky Way sits near the center of it. 2 billion light-years of relative emptiness surrounding us in every direction. This has a consequence that matters for more than just our location. A civilization inside a void experiences a gentle gravitational pull from the denser walls surrounding it, a pull that accelerates the local expansion of space slightly relative to the cosmic average. If this effect is real and measurable, our local measurements of how fast the universe is expanding would come out higher than the global value predicted by models of the early universe. There is a number in cosmology that is currently causing serious problems, a discrepancy between two ways of measuring the expansion rate that has now reached the level physicists use to declare a discovery. We will come to it in detail, but the void we live in may be part of the reason it exists. Our address in the universe, it turns out, is not a neutral vantage point. It may be shaping what we see. The visible matter, all the gas, stars, and galaxies, is not what drives the large-scale structure of the universe. It rides on something else, something invisible, something that has never been directly detected despite decades of effort and billions of dollars of experimental equipment designed specifically to find it. 85% of all matter in the universe is dark matter, not dim matter, not cold matter, not matter organized in some unfamiliar way that our instruments have simply not yet found. Dark matter does not interact with light at all. It does not emit radiation, absorb radiation, or reflect it. It has no electromagnetic signature of any kind. Every instrument humanity has ever built, every telescope, every radio dish, every X-ray observatory, every optical camera, works by detecting light in one form or another. Dark matter is invisible to all of them. The only evidence for its existence is gravitational, and that evidence is overwhelming. The first person to take it seriously was Fritz Zwicky, working at Caltech in 1933. Zwicky was studying the Coma Cluster, a massive concentration of galaxies roughly 320 million light-years from Earth, and he was measuring the speeds at which the individual galaxies within the cluster were moving relative to one another. The logic was straightforward. The faster the galaxies are moving, the more mass must be holding them together. If they were moving faster than the visible mass of the cluster could account for gravitationally, they should fly apart. They should not remain a cluster at all. The galaxies were moving far too fast. Orders of magnitude faster than the visible stars and gas could explain. Zwicky calculated that there must be additional mass, invisible mass, providing the extra gravitational glue. He called it Dunkel Materie, dark matter. The astronomical community largely ignored him for 4 decades. Then, Vera Rubin changed the picture. Rubin was working at the Carnegie Institution of Washington in the 1960s and 70s, studying the rotation of stars within individual spiral galaxies, not galaxy clusters, but single galaxies, measured star by star. The physics seemed simple. In a solar system, the outer planets orbit more slowly than the inner ones, because most of the mass is concentrated at the center. A galaxy, where most of the visible stars are also concentrated toward the center, should behave the same way. Stars near the edges should orbit more slowly than stars near the core. This is what Newton's laws predict. This is what every model assumed. It was not what Rubin found. The rotation curves were flat. Stars at the outer edges of galaxies were orbiting at essentially the same speed as stars near the center, sometimes faster. The further out you looked, the more wrong the predictions became. Rubin measured this in galaxy after galaxy, working with her colleague W. Kent Ford. The result was consistent, unambiguous, and deeply uncomfortable. Galaxies contain far more mass than the stars and gas we can see, distributed in a vast halo extending well beyond the visible disk. The mass we cannot see outweighs the mass we can see by a factor of several to 1. This confirmed, with far greater precision and at a far more accessible scale than Zwicky's cluster data, that dark matter is real. The evidence did not stop there. General relativity tells us that mass bends the path of light passing near it. The more mass, the greater the bending. This effect, called gravitational lensing, allows astronomers to map the distribution of mass in a region by observing how background galaxies are distorted by the foreground mass. When this technique is applied to galaxy clusters, the mass inferred from the lensing is consistently and dramatically larger than the mass visible in stars and hot gas. The most compelling single piece of evidence came from a system known as the Bullet Cluster, a pair of galaxy clusters caught in the act of colliding. When galaxy clusters collide, the hot gas that fills them, which makes up most of their ordinary matter, is slowed by electromagnetic interactions between the particles. It lags behind. The individual galaxies, which are mostly empty space, pass through each other relatively unimpeded, and the dark matter, which does not interact electromagnetically at all, passes straight through as if nothing had happened. The Chandra Space Observatory imaged the hot gas in X-ray, showing it piled up at the point of collision. The dark matter, mapped separately through gravitational lensing, had continued forward, separated from the gas, now spatially distinct from it. This was not a measurement of missing mass. It was a direct observation of a component of matter behaving differently from ordinary matter in a collision. Dark matter does not interact with itself or with ordinary matter the way atoms do. It has its own dynamic. It passes through obstacles that stop everything else. So what is it? Here is where the confidence ends. The leading theoretical candidates have been the weakly interacting massive particles, WIMPs, hypothetical particles, predicted by extensions of the standard model of particle physics, that should have masses in the range of tens to hundreds of times that of a proton, and that interact with ordinary matter through the weak nuclear force and gravity only. If they exist, they should occasionally collide with atomic nuclei in sufficiently sensitive detectors. For decades, that prediction has driven some of the most sophisticated experimental programs in physics. The Xenon 1T experiment, housed in the Gran Sasso underground laboratory beneath the Apennine Mountains in Italy. PANDX, located in the Jinping Underground Laboratory in China. Lux Zeppelin, in the Sanford Underground Research Facility in South Dakota. Detectors built inside mountains, shielded by kilometers of rock from cosmic ray background radiation, capable of registering the recoil of a single atomic nucleus. They have been running for years. They have found nothing. Some researchers have proposed alternatives: axions, sterile neutrinos, primordial black holes formed in the early universe. None has been confirmed. Mordechai Milgram at the Weizmann Institute proposed in 1983 that the problem might be solved not by adding invisible matter, but by modifying gravity itself. His modified Newtonian dynamics works remarkably well at the scale of individual galaxies, reproducing the flat rotation curves without any dark matter at all. But it fails at the scale of galaxy clusters. It cannot reproduce the Bullet Cluster observations. It cannot produce the cosmic web. No single modification of gravity has succeeded across all scales simultaneously. Dark matter is there. The universe does not work without it. And we have not the faintest idea what it is. Dark matter makes up approximately 27% of the total energy content of the universe. All the ordinary matter, every star, every planet, every atom of gas between the galaxies, every molecule of water, every human being alive, and every human being who has ever lived, makes up approximately 5%, which leaves 68% unaccounted for. That 68% has a name: dark energy. And if the story of dark matter is the story of an invisible substance we know is there but cannot identify, the story of dark energy is stranger still, because dark energy is not a substance at all, in any ordinary sense. It is a property of space itself, and it is tearing the universe apart. To understand how we found it, you need to understand what we expected to find. By the late 1990s, the expansion of the universe was well established. Hubble had discovered it in the 1920s. Every galaxy beyond the local group is receding from us, not because the galaxies are moving through space, but because the space between us and them is stretching. The further away a galaxy is, the faster it is receding, because there is more expanding space between us and it. This was not controversial. It was one of the most solidly established facts in cosmology. What was still open was the question of whether that expansion was slowing down, and by how much. Gravity should be decelerating it. All the matter in the universe attracts all the other matter, and that mutual attraction should be applying a brake to the expansion over time. The universe might eventually slow, stop, and recollapse, the big crunch, or it might expand forever, but at a diminishing rate. The specific answer depended on how much matter there was, but deceleration itself seemed certain. Nobody seriously questioned it. In 1998, 2 independent teams of astronomers set out to measure the deceleration directly using a particular type of exploding star. Type 1. A supernovae occur when a white dwarf, the dense remnant of a dead star, accumulates enough mass from a companion to exceed a critical threshold and detonate in a thermonuclear explosion. Because the detonation is triggered by a fixed mass threshold, the explosions all reach very similar peak brightnesses. They are not identical, but the variations are well understood and can be corrected for. This makes them extraordinarily useful as what astronomers call standard candles, objects of known intrinsic luminosity that can be used to calculate distances by comparing how bright they appear from Earth to how bright they actually are. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rees, then at Berkeley, both used this technique to look at supernovae in distant galaxies, measuring how far away those galaxies were and comparing that to how fast they were receding. The goal was to plot the deceleration of the expansion across cosmic time. The supernovae were in the wrong place, not by a little. They were significantly dimmer than expected, which means they were significantly farther away than a decelerating universe would have placed them. The expansion was not slowing down, it was speeding up. Something was driving space apart at an accelerating rate, not despite gravity, but in addition to it, and winning. The result was published, checked, cross-checked, and eventually accepted. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011. The discovery was not merely surprising, it was a fundamental revision of what the universe is. The force driving the acceleration has been named dark energy, with full awareness of how little that name actually says. It is dark because we cannot observe it. It is energy because it has a measurable effect. Beyond that, the naming admits ignorance. We do not know what dark energy is, where it comes from, or why it has the value it has. The most mathematically elegant description treats dark energy as a property of the vacuum, a baseline energy density of empty space that is not zero. Einstein had actually included such a term in his original equations of general relativity in 1917, calling it the cosmological constant, using it to produce a static universe because the alternative, an expanding or contracting universe, seemed physically implausible to him at the time. He reportedly called the cosmological constant his greatest blunder after Hubble demonstrated that the universe was in fact expanding. But the 1998 observations suggested the constant might be real after all. Not as a way of holding the universe static, but as the property of the vacuum that is causing its expansion to accelerate. What this means physically, why the vacuum should have this energy density, and why it has exactly the value it has, rather than a value enormously larger or smaller, remains entirely unexplained. The theoretical prediction for the cosmological constant from quantum field theory differs from the measured value by somewhere between 50 and 120 orders of magnitude, depending on the assumptions made. This is often described as the worst prediction in physics. It is also one of the deepest unsolved problems in science. The practical consequence of dark energy's dominance is this. Beyond a certain distance from the Milky Way, galaxies are already receding from us faster than the speed of light. Not because they are moving through space faster than light, relativity forbids this, but because the space between us and them is expanding faster than light can cross it. A photon emitted from one of those galaxies right now, heading in our direction, is on a treadmill that is accelerating away from it. The photon will never arrive. That galaxy is lost to us permanently, not because it is too far away today, but because the distance between us is growing faster than any signal can ever bridge. The universe contains, right now, galaxies that we will never see. Galaxies that have already emitted their last photon that will ever reach us. Galaxies sliding silently over a horizon made not of distance, but of physics. And there are more of them with every passing second. So let us build the address, the full address, every layer, from where you are sitting right now to the outermost boundary of what has ever been observed. Each layer will dwarf the one before it. That is the point. You are on a planet, a rocky planet, 12,742 kilometers in diameter, the third of 8 in a system orbiting a single ordinary star. The solar system, in the broadest sense, including the Oort cloud with its diffuse halo of comets, extends roughly 1.5 to 2 light-years from the Sun. That is a small bubble around a single star. One star among 200 to 400 billion in the galaxy. The Milky Way is 100,000 light-years across. You are roughly 26,000 light-years from its center, in a minor spiral spur, orbiting that center at 220 kilometers per second. The Milky Way is not alone. It sits within a gravitationally bound collection of roughly 100 galaxies called the Local Group, spread across a volume approximately 10 million light-years across. The two largest members are the Milky Way and Andromeda, separated by about 2.5 million light-years. The Local Group also contains the Triangulum Galaxy, the Large and Small Magellanic Clouds, two small irregular galaxies visible to the naked eye from the southern hemisphere, and dozens of smaller dwarf galaxies orbiting the two dominant members. Together, they form a gravitational family, bound by their collective mass, slowly interacting across deep time. The Local Group is itself part of something larger, the Virgo supercluster, a structure approximately 110 million light-years across, contains roughly 100 galaxy groups and clusters, with the Virgo cluster itself at its gravitational heart. The Virgo cluster holds more than 1,300 galaxies and sits approximately 54 million light-years from the Milky Way. For most of the 20th century, the Virgo supercluster was understood to be the structure containing the Milky Way. In 2014, that understanding was revised. Brent Tully, at the University of Hawaii, and his colleagues published an analysis that mapped the flow of galaxies through space, not just their positions, but the direction and speed at which they are moving. When they plotted those flows, they found that the Milky Way, the Virgo supercluster, and dozens of other nearby structures were all part of a single gravitational basin, a region in which all galaxy flows converge toward a common center. They named this basin Laniakea, from the Hawaiian for immense heaven. Laniakea spans 520 million light-years and contains approximately 100,000 galaxies. All of them are flowing, slowly, toward a gravitational attractor at its heart, a region in the direction of the constellation Centaurus that has been pulling the Milky Way and its neighbors for billions of years. Alan Dressler at the Carnegie Observatories was part of the team that first identified this pull in the 1980s. Working with 6 colleagues, a group later nicknamed the Seven Samurai, Dressler mapped the peculiar motions of galaxies across a large swath of the sky and found that hundreds of them were streaming in the same direction at approximately 600 kilometers per second. Something with enormous gravitational influence was drawing them. They named it the Great Attractor. The Great Attractor sits behind the disk of the Milky Way, in a region of sky that our own galaxy obscures. Astronomers call it the zone of avoidance. X-ray and infrared observations have partially penetrated that obscuration and revealed the Norma cluster, a massive galaxy cluster at approximately the right position. But the Norma cluster alone cannot account for all the pull. The gravitational influence almost certainly extends to the Shapley supercluster, 650 million light-years away, one of the densest concentrations of matter in the observable universe. The Milky Way is falling toward it. It has been falling toward it for billions of years. It will never arrive, because the expansion of the universe is pushing the destination away faster than gravity can close the gap. Laniakea itself is part of a larger structure still, the Pisces-Cetus supercluster complex, a galactic filament approximately 1 billion light-years long, threading through the cosmic web and containing Laniakea alongside several other superclusters. 1 billion light-years, our largest identified structure. Inside an observable universe 93 billion light-years across. The Pisces-Cetus supercluster complex, 1 billion light-years of galaxies, gas, and dark matter, is roughly 1% of the observable universe's diameter. Everything from the Milky Way to the supercluster complex to the observable universe is nested, each layer containing the previous one, each layer larger by a factor that strains comprehension. The address runs from a planet to a solar system, to a galaxy, to a local group, to a supercluster complex, to the observable universe. 7 layers, each one dwarfing the last. And then the question becomes, what is the observable universe, exactly? What does that boundary mean? And is it the end? The observable universe is 93 billion light-years across. You have heard this number before in this video, and it is worth pausing now to make it precise, because the reasoning behind it is stranger and more revealing than the number alone suggests. The universe is approximately 13.8 billion years old. A straightforward reading of this would suggest the farthest we can see is 13.8 billion light-years. The distance light can travel in that time. This is wrong. Here is why. When a distant galaxy emitted light 13 billion years ago, it was much closer to us than it is today. Light is not instantaneous. It travels at a fixed speed. And while that light was in transit, while it was crossing the space between that ancient galaxy and us, the space itself was expanding. The galaxy was being carried further away by the expansion of the universe. By the time the light arrives at our telescopes, the galaxy that sent it has been carried to a commoving distance of roughly 46 billion light-years. This is why the observable universe has a radius of 46 billion light-years, despite being only 13.8 billion years old. The universe expanded while the light was traveling. The outermost surface of the observable universe, the farthest thing we can see, is the cosmic microwave background. This is not a galaxy or a star. It is radiation. It was released approximately 380,000 years after the Big Bang, during an event called recombination. Before recombination, the universe was too hot for atoms to exist. Electrons and protons were separate, forming a dense plasma through which photons could not travel freely. They were constantly scattered, trapped in the fog. The universe was opaque. Then, as expansion caused the temperature to drop below roughly 3,000 degrees, electrons and protons combined into neutral hydrogen atoms for the first time. The fog lifted. Photons that had been trapped in the plasma were suddenly free to travel. They have been traveling ever since, expanding and cooling with the universe, their wavelengths stretching from the optical into the microwave range over 13 billion years of cosmic expansion. That radiation, the afterglow of the Big Bang, surrounds us in every direction at a temperature of approximately 2.7 Kelvin. The cosmic microwave background. Its existence was detected accidentally in 1964. Arno Penzias and Robert Wilson, working on a microwave communications antenna at Bell Labs in New Jersey, found a persistent hiss of radio noise that refused to go away, regardless of how they calibrated their equipment or what direction they pointed the antenna. It was coming from everywhere equally. They initially considered the possibility that bird droppings in the antenna horn were generating the interference. They were not. The signal was the oldest light in the universe, and Penzias and Wilson were the first people to hear it. They received the Nobel Prize in Physics in 1978. The CMB is not merely a boundary marker, it is a message. The tiny temperature fluctuations imprinted in it, variations of roughly 1 part in 100,000 across the sky, encode the full acoustic history of the early universe. In the first 380,000 years, the hot plasma was ringing, waves of compression and rarefaction, sound waves in a cosmological sense, driven by the competing forces of gravity and radiation pressure. When recombination froze the plasma, those waves were frozen too, locked into the distribution of matter across the sky. The pattern of those frozen waves, the baryon acoustic oscillations, tells cosmologists everything: the geometry of space, the composition of the universe, its age, the amplitude of the initial density fluctuations. The entire cosmological parameter set encoded in a single map. The ESA Planck satellite produced the most precise measurement of this map ever achieved, completing its observations in 2013. The data it returned constrained the age of the universe to 13.8 billion years. The expansion rate, the dark matter fraction, the dark energy fraction, and the flatness of space, all from the pattern of temperature fluctuations in light released 400 times more recently than the first galaxies. The first satellite to map the CMB in any detail was COBE, the Cosmic Background Explorer, launched by NASA in 1989, which confirmed the blackbody spectrum of the radiation and detected the first hints of temperature anisotropy. COBE's principal investigators, George Smoot and John Mather, received the Nobel Prize in Physics in 2006 for that work. Planck's measurements represent the culmination of a 30-year program of increasing precision, and what they reveal is a universe whose large-scale properties can be read directly from a map of light that is 13.4 billion years old. Beyond the CMB, there is no electromagnetic information available. The universe before recombination was opaque to light. That wall of radiation is the ultimate horizon of observation. And beyond the event horizon, the distance beyond which light emitted today will never reach us, there is a second, harder boundary. As the expansion accelerates, galaxies currently visible will eventually be carried past the event horizon. Their light will redshift towards zero energy, undetectable. The CMB itself will stretch beyond the range of any conceivable instrument. In hundreds of billions of years, a civilization in this galaxy will look out at a sky containing only the local group, the few dozen galaxies gravitationally bound tightly enough to resist the expansion. Every other galaxy will have vanished. The CMB will be gone. The evidence for the Big Bang will be physically inaccessible. Their cosmology will be necessarily, inescapably wrong, not through any failure of intelligence or method, but because the universe will have hidden its own history. We live in the only era during which the story can be read. The CMB is still detectable. The distant galaxies are still visible. The universe has not yet swallowed its own evidence. This is not a coincidence we should take for granted. We have been moving outward, from the solar system to the galaxy, from the galaxy to the web, from the web to the observable boundary. Now let us move in the other direction, not in space, but in time. Because understanding what the universe looks like today requires understanding what it passed through to get here. And there is a period in cosmic history that is rarely discussed with the attention it deserves. The cosmic microwave background was released 380,000 years after the Big Bang. Before that, the universe was opaque. After recombination, when the plasma cleared and the CMB was released, the universe became transparent, but it did not become luminous. The hydrogen gas that filled all of space was neutral. There were no stars yet. There were no galaxies. There were no sources of light of any kind. The universe existed. It expanded. The neutral hydrogen drifted in the dark, and nothing happened for what is estimated to have been somewhere between 100 and 200 million years. Astronomers call this period the cosmic dark ages. Not as a metaphor, the universe was literally dark, producing no photons, emitting no radiation in any wavelength that any instrument would have detected. If you could have placed an eye anywhere in the universe during this era, in any direction, you would have seen nothing. The darkness was total, unbroken, the longest night in the history of everything. Then, somewhere, a cloud of gas became dense enough to collapse under its own gravity, and the first star ignited. These first stars, classified as population 3 stars, are among the most consequential objects in the history of the universe and among the least directly observed. We have never seen one. No telescope currently in operation has the sensitivity to resolve an individual population 3 star at the distances involved. What we know about them comes almost entirely from theory. The theory is compelling. Volker Brom at the University of Texas at Austin and Richard Larson at Yale, among others, built the theoretical framework for how these stars must have formed. The key constraint is chemistry, or rather, its absence. The gas available to form the first stars was primordial, almost entirely hydrogen and helium, the elements produced in the first 3 minutes after the Big Bang. There were no heavier elements, no carbon, no oxygen, no iron, none of the molecules that modern star-forming clouds use to radiate away heat and cool down efficiently. Without efficient cooling, a collapsing cloud cannot fragment into the many small pieces that produce ordinary stars. Instead, the collapse tends to produce a small number of extraordinarily massive objects. Estimates of population 3 star masses range from tens of solar masses to possibly several hundred or even over 1,000, orders of magnitude larger than typical stars forming today. Mass determines everything for a star. The more massive it is, the hotter it burns, the brighter it shines, and the faster it dies. A star like our Sun will live for roughly 10 billion years. A star 10 times more massive lives for tens of millions of years at most. A population 3 star near the upper end of the mass range would have burned for perhaps a few million years before ending in a catastrophic explosion. Sufficiently massive stars are thought to end as pair instability supernovae, a type of explosion with no analogue among stars forming today, in which the core reaches temperatures high enough to spontaneously produce electron-positron pairs, destabilizing the entire structure and triggering a runaway thermonuclear detonation that destroys the star completely. These explosions scatter the star's entire mass into the surrounding intergalactic medium. This is where the chemistry of the universe begins. The iron in your blood, the calcium in your bones, the oxygen in every breath you take. Every heavy element that exists anywhere in the observable universe was built inside a star and released by its death. The population 3 supernovae were the first such events. They seeded the intergalactic medium with the first metals, the first elements heavier than hydrogen and helium, from which the second generation of stars, the first planets, and eventually the first conditions for life could form. As the first stars ignited and died, and as the first galaxies assembled around concentrations of dark matter, the universe underwent a transformation that took hundreds of millions of years. The ultraviolet radiation pouring from these early sources began to ionize the surrounding neutral hydrogen, stripping electrons from atoms, reversing recombination, clearing the fog that had filled the universe since 380,000 years after the Big Bang. This is the epoch of rhionization, the period during which the universe transitioned, patchily and progressively, from a fog of neutral hydrogen back to the ionized state it had been in during its earliest moments. Brant Robertson at the University of California, Santa Cruz has done much to constrain the timeline of this process, using observations from the Hubble Space Telescope's deep field campaigns. The transition appears to have been largely complete by around 950 million years after the Big Bang, having begun as early as 370 million years after, at redshifts between 6 and 12. The James Webb Space Telescope was designed, in part, to see into this era. Its infrared sensitivity allows it to detect light from objects at redshifts above 10, where the expansion of the universe has stretched visible and ultraviolet wavelengths far into the infrared, a domain inaccessible to any previous instrument. Webb is the first telescope capable of observing individual galaxies within the epoch of rhionization with spectroscopic resolution sufficient to characterize their chemistry. And what it has found there is deeply unexpected. But before we arrive at that, consider one anomaly that connects the population 3 mystery directly to the most distant confirmed galaxy ever observed: nitrogen, an element produced through nuclear fusion cycles in stellar cores, an element that normally requires several generations of stellar evolution to accumulate in detectable quantities. It was found, in surprising abundance, in a galaxy existing just 280 million years after the Big Bang. Before, in theory, there had been enough time for even a single full stellar generation to complete. The first light left questions that the best telescope ever built is only beginning to answer. The James Webb Space Telescope launched on Christmas Day, 2021. It had been in development for 25 years. It cost approximately $10 billion. Its primary mirror is 6.5 meters across, made from 18 hexagonal segments of polished beryllium coated in a microscopically thin layer of gold, a design chosen because gold reflects infrared light with exceptional efficiency. It was positioned not in low Earth orbit, where the Hubble Space Telescope operates, but at the second Lagrange point, a gravitationally stable location 1.5 million kilometers from Earth, where the combined gravity of the Earth and Sun holds the telescope in a fixed orientation relative to both. A sunshield the size of a tennis court keeps the mirror and instruments perpetually in shadow, cooling them to temperatures near absolute zero, necessary because the infrared radiation Webb is designed to detect is also emitted by anything warm, including the telescope itself. NIRCam, NIRSpec, and MIRI, its three primary science instruments, together cover wavelengths from near ultraviolet through the near infrared to the mid-infrared. This range was chosen with a specific scientific purpose. At redshifts above 10, the expansion of the universe has stretched light that was originally emitted in the ultraviolet into the infrared. Only an infrared telescope, operating with Webb's precision and sensitivity, can see those sources directly. Before Webb began science operations, the predictions were specific and confident. At redshifts above 10, in the first 500 million years after the Big Bang, galaxies would be small, dim, simple, and chemically primitive. They would contain only the most basic elements. They would be in the early stages of assembly, not yet mature in any structural or chemical sense. The sky at redshift 12 to 15 was expected to be nearly empty of detectable bright sources. The pre-launch consensus was not a casual estimate. It was the output of the standard cosmological model, lambda CDM, applied to the conditions of the early universe and tested against every previous observation. It was the best understanding cosmology had built in decades of work. It was wrong. Within its first year of science operations, Webb identified dozens of galaxy candidates at redshifts above 10. Several were confirmed spectroscopically, meaning their distances were determined not from photometric color estimates, but from precise measurements of their spectra, eliminating ambiguity. The number density of bright galaxies at redshifts of 12 to 15 is more than 100 times larger than the pre-launch models predicted. Not 10% more, not double, 100 times more. The universe's earliest observable epoch is not sparsely populated. It is crowded with luminous, massive, apparently mature structures that have no straightforward explanation under the model that was supposed to describe them. The most extreme confirmed example carries the designation JADES-GS-Z14-0. Its redshift, 14.32, was confirmed spectroscopically by Rohan Naidu and colleagues at the MIT Kavli Institute in 2024. At that redshift, the light arriving at Webb's mirror has been traveling for over 13.5 billion years. We see this galaxy as it was just 280 million years after the Big Bang, when the universe was roughly 2% of its current age. It should not exist, not in its current form. It is remarkably luminous, far brighter than models allow at that epoch. It is extremely compact, with an effective radius of roughly 240 light-years. Its spectrum reveals elevated nitrogen, an element that normally requires multiple stellar generations to build up. Each cycle of starbirth and death enriching the surrounding gas before the next generation forms. 280 million years is not enough time for that, or should not be. And the galaxy appears to have already begun ionizing the neutral hydrogen surrounding it, clearing a bubble in the cosmic fog that models said could not yet exist at that redshift. Jacob Leger at Penn State, a member of the research team, described what Webb is revealing as a growing chasm between theory and observation in the early universe. That is careful language for something that is, in practice, genuinely alarming for the Standard Model. JADES-GS-Z14-0 is not alone in its strangeness. A galaxy named Zhulong, identified at a redshift of approximately 5.2, existing around 1 billion years after the Big Bang, is a grand design spiral, fully formed spiral arms, a mature central bulge, a total stellar mass of approximately 100 billion solar masses. Spiral structure is not assembled quickly. It requires repeated gravitational interactions, disk settling, and the kind of dynamical evolution that takes time. Time that this galaxy, at that redshift, had not had. It looks like a galaxy that should be several billion years old. It is not. Then there is a population of compact, red, massive galaxies at redshifts between 4 and 9, studied by Ivo Labbé at Swinburne University of Technology and colleagues in a paper published in Nature in 2023. Their apparent stellar masses, in some cases between 10 and 100 billion solar masses, exceed what lambda CDM permits at those epochs. Michael Boylan-Colchin at the University of Texas at Austin quantified the problem precisely. If the mass estimates are confirmed, these galaxies contain more stellar mass than could have formed even if every atom of available gas had been converted into stars at 100% efficiency from the very first moment of the Big Bang. They do not merely challenge the model, they contradict it. The proposed explanations are numerous, and none is satisfying. Perhaps star formation in the early universe was dramatically more efficient than modern observations suggest. Perhaps a brief burst of additional dark energy in the first few 100 million years accelerated the collapse of structures. Perhaps some of the apparent stellar mass is contaminated by light from active galactic nuclei at the centers of these galaxies, inflating the estimates. Perhaps modifications to our understanding of dark matter are needed. No single explanation accounts for all the anomalies simultaneously. The field is actively, honestly, and in some cases, uncomfortably unsettled. The Big Bang is not in question. The CMB, the abundance of light elements, the observed expansion of the universe, these pillars stand. What is cracking is the timeline. The sequence of events lambda CDM predicts should follow the Big Bang is not what Webb is seeing. And that crack connects directly to a crisis that began not in the deep past, but in the precision measurements of the present. There is a number at the heart of cosmology called the Hubble constant. It measures the rate at which the universe is expanding, specifically, how fast 2 points in space are moving apart as a function of the distance between them. The unit is kilometers per second per megaparsec, for every 3.26 million light-years of distance between two objects. The space between them is expanding at a rate of h0 kilometers per second, where h0 is the constant you are trying to measure. Get this number right, and the age of the universe, its size, and its ultimate fate all follow from it. Get it wrong, and the foundation of cosmology shifts. For decades, two independent ways of measuring the Hubble constant were developed, and for decades the assumption was that as precision improved, they would converge. They have not. They are moving apart. The first method looks at the oldest light in the universe. The ESA Planck satellite mapped the cosmic microwave background in extraordinary detail, and from the precise pattern of temperature fluctuations, the frozen acoustic oscillations we discussed earlier, combined with the lambda CDM model, cosmologists calculated the expansion rate. The Planck result is approximately 67.4 kilometers per second per megaparsec. The Atacama Cosmology Telescope, a separate ground-based instrument operating in the Chilean Andes, independently produced a consistent value of approximately 68.2. The early universe route is stable, repeatable, and precise. The second method measures the expansion directly, using a chain of distance measurements called the cosmic distance ladder. The first rung uses geometric parallax, the tiny apparent shift in a nearby star's position as Earth orbits the Sun, to establish precise distances to the closest stars. The second rung uses those calibrated distances to characterize Cepheid variable stars whose intrinsic brightness is tied to their pulsation period. Measure a Cepheids period, calculate its true luminosity, compare to its apparent brightness, and you have its distance. The third rung uses Cepheids in distant galaxies to calibrate Type 1a supernovae, the standard candles we use to discover dark energy. And from those, the expansion rate of the local universe is measured directly. Adam Rees at Johns Hopkins University, who shared the Nobel Prize in Physics for the discovery of cosmic acceleration, has led the SH0ES team in refining this measurement for 2 decades. Their 2022 result placed the Hubble constant at 73.04 kilometers per second per megaparsec, with an uncertainty of just over 1%. That 1% precision is not a casual number. It represents years of accumulated calibration, systematic checks, and remeasurement. The gap between 67 and 73 is small in absolute terms. In precision cosmology, it is enormous. If the early universe value is correct, the local measurements are wrong by a margin that should be essentially impossible given their stated uncertainties. If the local value is correct, the model used to derive the early universe value is missing something fundamental. Between 2023 and 2025, the SH0ES team used James Webb to reobserve the Cepheid variable stars at the base of their distance ladder. Webb's sharper infrared imaging eliminated concerns about dust contamination and crowded star fields that critics had raised as possible sources of systematic error. The result? The Hubble Space Telescope data was correct. The Cepheids are where and how bright the earlier measurements said they were. The local value of approximately 73 is not an artifact of instrument limitations. The TD Cosmo collaboration, a team using an entirely different approach called time delay cosmography, provided further independent confirmation. When a massive galaxy sits between us and a distant quasar, the galaxy's gravity bends the quasar's light into multiple images. Because each bent path has a different length, the images flicker at slightly different times as the quasar varies in brightness. By measuring those time delays and modeling the mass distribution of the lensing galaxy, the Hubble constant can be derived with no reference to Cepheids or supernovae whatsoever. In December of 2025, the TDCOSMO result matched the local measurement, not the CMB value. Every new independent method that measures the local expansion rate arrives at approximately the same answer. And that answer disagrees with the model built on the earliest light in the universe. As of late 2025, the statistical significance of the discrepancy has reached 5 sigma. In physics, 5 sigma is the threshold used to declare a discovery, the same standard used to confirm the Higgs boson at CERN in 2012. A 5 sigma result means the probability that the gap is due to random chance is less than 1 in 3.5 million. The Hubble tension is not a measurement fluctuation. It is not an unresolved instrumental issue. It is a real, worsening, statistically confirmed discrepancy in the best model cosmology has built. Proposed resolutions have multiplied. Early dark energy, a brief burst of additional energy density in the universe before recombination, could shift the sound horizon imprinted in the CMB and raise the early universe Hubble value toward the local measurement. But early dark energy models that fix this tension tend to create new mismatches with other features of the CMB data. Carsten Jadamczyk at the Université de Montpellier and Levon Pogosyan at Simon Fraser University proposed in 2021 that primordial magnetic fields in the early universe could have altered the recombination process, changing the derived CMB value in the right direction. Their analysis has received significant attention, but not yet universal acceptance. The KBC void, the underdense region around the Milky Way we discussed earlier, provides a geometric explanation that requires no new physics, only an unusual cosmic address. New neutrino species, modified gravity at cosmological scales, and interacting dark energy have all been explored. None achieves full resolution. None accounts for all the anomalies simultaneously without creating new problems elsewhere. The Lambda CDM model which has survived every observational test for 25 years, is for the first time showing cracks that cannot be explained away. Whether those cracks require new fundamental physics, a modification to the model at some deep level, or whether they will eventually be resolved by some combination of small systematic corrections, is not yet known. The answer will come from more measurements, more independent methods, more precision. But the question is real, and it is open. There is something worth sitting with here. The Hubble constant is not an obscure technical parameter. It is the number from which the age of the universe is derived. It is the number on which the size of the observable universe depends. If the true value is closer to 73 and not 67, the universe is younger than the standard model says. If the standard model survives at 67, the local measurements carry a subtle unidentified flaw that the best instruments in the world have not yet found. The gap of 6 units in a single number may be the most consequential unresolved question in cosmology today, because resolving it will almost certainly require changing something about what we think we know, in a field where changes of that magnitude do not come quietly. What lies on the other side of the observable boundary is a question that cannot be answered by observation. We cannot look past the cosmic microwave background. We cannot send a signal beyond the event horizon and receive a reply. Everything we know about the region beyond the 46 billion light-year radius of the observable universe is inferred from the physics we observe within it and the logical consequences of that physics extended outward. But there is one measurement that tells us something important. The universe is flat. In cosmology, flatness refers to the geometry of space, not its shape in the everyday sense, but the way distances and angles behave within it. A flat universe is one in which the angles of a triangle sum to exactly 180 degrees, and parallel lines never converge or diverge. A positively curved universe, like the surface of a sphere, would have triangles whose angles sum to more than 180 degrees, and could in principle be finite. A negatively curved universe would have triangles summing to less. The Planck satellite's measurement of the CMB has established the geometry of the observable universe to be flat to within 0.4%. This has an implication. For our 93 billion light-year observable patch to appear as flat as it does, for the curvature to be undetectable at that scale, the full universe must be vastly larger than the portion we can see. A basketball appears flat to an ant because the curvature is too gradual to detect at that scale. The universe appears flat to us for the same reason. An analysis by researchers at Oxford placed a conservative lower bound on the full universe's diameter at a minimum of 250 times the observable portion, at least 23 trillion light-years across. That is the conservative estimate. Alan Guth at MIT, who proposed the theory of cosmic inflation in 1981, has estimated the implications more aggressively. Inflation, the exponential expansion of the universe in the first fraction of a second after the Big Bang, is the mechanism that produced the flatness we measure. In an inconceivably brief interval, a region smaller than a proton expanded by a factor of at least 10 to the power of 26. If that process occurred, the total universe is not merely 250 times larger than the observable portion. It is, under Guth's estimates, approximately 10 to the power of 23 times larger. A 1 followed by 23 zeros, a number for which no useful analogy exists. And that assumes inflation had a definite end. If the universe is genuinely geometrically flat, not just close to flat, but exactly flat, the implication is more extreme still. A perfectly flat universe is infinite. It extends in every direction without limit, without boundary, without center. In an infinite universe, every configuration of matter that is physically possible occurs. Not once, but infinitely many times. There are no copies of you in this framing, because there is no original. There are infinite instances of every arrangement of atoms that quantum mechanics permits, scattered across a space so large that the concept of distance between them loses meaning. This is not speculation. It is a logical consequence of the measurements. Whether it is also true is a different question, and one that cannot be resolved from within an observable bubble. What we can say is this: the universe we can see, all 93 billion light-years of it, all 2 trillion galaxies, all the filaments and voids and clusters, and the one star with the one inhabited planet, and all the science that planet has produced, may be, in the full context of what exists, not even a rounding error. We are somewhere. We just cannot begin to say how far from everything else. If the observable universe is not the full universe, if what lies beyond the 46 billion light-year horizon is vastly, incomprehensibly larger, the question becomes, what is the rest of it like? Is it more of the same? Or is it different in ways we cannot yet conceive? The answer depends on which version of cosmic inflation happened, and one version leads somewhere that most people, when they hear it for the first time, find deeply uncomfortable. The inflationary framework does not simply predict that the universe underwent rapid early expansion. The quantum field responsible for that expansion, called the inflaton field, is subject to quantum fluctuations. In most regions of space, the field eventually decays and inflation ends, allowing matter and radiation to form in a Big Bang. But in some regions, quantum fluctuations cause the field to remain high, maintaining inflation indefinitely. Those regions continue to expand exponentially, while other regions around them drop out of the inflationary phase and produce their own Big Bangs. This is the core of eternal inflation. Once inflation starts, it does not stop everywhere. It stops in pockets, bubbles of space that exit the inflationary phase, expand from a hot, dense state, and evolve into universes. Our universe on this model is one such pocket. It began with a Big Bang, when a region of the eternally inflating background happened to tunnel into a lower energy state. Other regions did the same, before and after, and the inflating background between those pockets continues to expand faster than new pockets form, ensuring that the process never terminates. Andre Linde at Stanford University formalized this picture in his chaotic inflation model in 1983. Alexander Vilenkin at Tufts University independently developed the tunneling nucleation model, which produces a similar result through a slightly different mechanism. Alan Guth, whose original inflationary proposal set the whole framework in motion, has also contributed extensively to its elaboration. All three models arrive at the same broad conclusion. Our universe is one bubble among an effectively infinite collection of bubble universes, each enclosed within an eternally expanding inflating background, each causally disconnected from all the others. No signal can pass between bubble universes. No light, no gravitational wave, no information of any kind. The causal disconnection is not a technological limitation. It is a consequence of the physics. Even if a civilization in our universe devoted all of its resources to sending a message to a neighboring bubble, the message could never arrive. The space between bubbles is expanding faster than any signal can cross it, and has been since before our universe began. The string theory landscape adds another layer to this picture. String theory, one of the leading candidates for a unified theory of physics, predicts that the fundamental constants of nature are not fixed. They depend on the configuration of extraspatial dimensions compactified at scales far below what any accelerator can probe, and there are an estimated 10 to the power of 500 distinct configurations, each corresponding to a different set of physical laws, different particle masses, different force strengths. In the multiverse framework, each bubble universe could settle into a different configuration, a different vacuum state, when inflation ends. The strength of gravity in one bubble might differ from ours. The mass of the electron might be different. The cosmological constant, which in our universe has the specific tiny value that permits galaxies to form rather than tearing the universe apart before structure can emerge, might take a vastly different value in another bubble, producing a universe of featureless radiation, or one that collapses within seconds. We observe the constants we observe, on this account, not because they are uniquely correct, but because they are the constants that permit observers to exist. In a bubble with a different cosmological constant, there would be no galaxies, no stars, no planets, no chemistry, and therefore no one to note the absence. This reasoning, called the anthropic principle, is either deeply profound or deeply unsatisfying, depending on your disposition. Its proponents argue it is a natural and unavoidable consequence of taking the physics seriously. Its critics argue that a framework which can explain any observation by appeal to a universe somewhere in which that observation would occur is not making a scientific prediction at all. Both positions are held by serious physicists. The debate is not settled, and may never be. There are hints, faint, contested, far below the threshold of confident claims, that the multiverse has left a mark on the CMB. If two bubble universes nucleated close together in the inflating background and their walls collided before our Big Bang, that collision would have imprinted a circular ring of anomalous temperature in the CMB. Several features in the CMB data have been proposed as candidates. A cold spot in the southern sky, a large-scale asymmetry in the power distribution. None exceeds 5 sigma. None has been universally accepted. But they exist at the edges of the data, suggestive and unresolved. In 2018, shortly before his death, Stephen Hawking co-authored a paper with Thomas Hertog proposing a reformulation of the multiverse using the holographic principle, a concept from string theory suggesting that the physics of a volume can be described by a theory on its boundary. Hawking and Hertog argued that this approach could reduce the infinite multiverse to a finite, mathematically tractable ensemble of possible histories, potentially subject to observational constraint through future gravitational wave observations. It was a serious attempt to make the multiverse falsifiable, to move it from philosophy into physics. Whether it succeeds is still being assessed. The multiverse sits exactly at the boundary between the two. It is the most extreme logical extension of the physics we have the most confidence in. It cannot currently be confirmed or ruled out. It may be the most important idea in cosmology. It may be untestable forever. What is certain is that if it is real, our universe is one island in an archipelago whose extent makes the observable universe look like a single grain of sand. What is also certain is that whether the multiverse exists or not, the question of what lies within our own observable universe, whether any of its 2 trillion galaxies host anything capable of looking back, is one of the oldest and most unanswered questions in science. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains, on average, somewhere between 100 billion and several hundred billion stars. The total number of stars in the observable universe is estimated at around 10 to the power of 24, a 1 followed by 24 zeros. Astronomers call this a septillion. Most of those stars have planets. Data from the Kepler Space Telescope and ground-based surveys suggest that the average number of planets per star is at least 1, and that rocky planets in the habitable zone, where liquid water could exist on a surface, are common. Conservative estimates place the number of potentially habitable worlds in the Milky Way alone at between 300 million and 10 billion. Scale that figure by 2 trillion galaxies. The number of potentially habitable worlds in the observable universe alone exceeds any figure that can be usefully expressed. And if the full universe is 10 to the power of 23 times larger than the observable portion, the total number of potentially habitable worlds is beyond any calculation. The universe is not lacking in real estate. And yet, no confirmed signal, no detected technosignature, no verified extraterrestrial contact of any kind has ever been recorded, despite decades of listening. The search for extraterrestrial intelligence has been scanning the sky for radio signals since the 1960s. No confirmed detection. We have looked for laser pulses, for anomalous infrared signatures, for the engineering scale structures that a civilization capable of harvesting stellar energy would presumably build. Nothing. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation turned to the possibility of extraterrestrial life. Fermi, known for making rapid back-of-the-envelope estimates, considered the age of the galaxy, the number of stars, the probability of planets, and the time a civilization would need to spread across the galaxy, even at modest speeds. His conclusion, delivered in a single question, has not been answered in the 75 years since. Where is everybody? A civilization expanding at even 1% of the speed of light, a fraction of what the physics of nuclear propulsion might eventually allow, could colonize the entire Milky Way in fewer than 10 million years. On a galaxy that is 13 billion years old, 10 million years is nothing. Any civilization that arose long enough ago and developed the capability for interstellar expansion should, by now, be everywhere. The evidence of its existence should be unmistakable, overwhelming, impossible to miss. The galaxy is silent. Robin Hanson at George Mason University formalized one class of explanation in 1998. The Great Filter. Somewhere between simple chemistry and a galaxy-spanning civilization lies a step so difficult, so improbable, that almost nothing gets past it. The question is where that filter sits on the timeline. If it is behind us, if the hard step was the emergence of life from non-living chemistry, or the development of eukaryotic cells, or the appearance of multicellular organisms, or consciousness, then we are among the vanishingly rare survivors, and the galaxy is mostly empty. If the filter lies ahead, if civilizations characteristically develop the capacity for self-destruction before they develop the capacity for interstellar presence, then the silence is not reassuring. It is a data point about our future. But there is a third possibility, and it is the one that this entire journey through the cosmos has been building toward. The universe is simply too large. The distances between stars within a galaxy are already paralyzing, as we established at the beginning of this journey. Our radio signals, everything humanity has broadcast into space since the early 20th century, have reached a sphere 125 light-years in radius, inside a galaxy 100,000 light-years across. At the scale of the Milky Way, our radio bubble is invisible. A message sent to the Virgo cluster, the nearest large collection of galaxies, would arrive 54 million years from now. The civilization that sent it would be long extinct before any reply could return. And between galaxy clusters, the situation is not merely difficult, it is geometrically irreversible. Dark energy is accelerating the expansion of space. Galaxy clusters beyond a certain distance are already receding faster than the speed of light, not moving through space faster than light, but carried apart by the expansion of the fabric itself. If another civilization exists in a galaxy cluster beyond our event horizon, their signals will never reach us, regardless of how powerful their transmitters are or how long they broadcast. The universe is actively working to separate its inhabitants, and it has been doing so since the moment it began. The silence may not be a mystery. It may be the answer. The universe is full, perhaps full of life, full of intelligence, full of civilizations asking the same question in their own languages on their own worlds. And every one of them is sealed inside their own observable bubble, surrounded by the same expanding isolation, staring at the same quiet sky, waiting for a reply that the laws of physics will not permit to arrive. That is not a comforting thought. It is an honest one. On the 14th of February 1990, Voyager 1 was 6 billion kilometers from Earth. It had finished its planetary mission. Its cameras were about to be powered down forever. Carl Sagan had spent months persuading NASA to do one final thing before they went dark: turn the camera around. Take one last picture, not of a planet, not of a moon, of home. The resulting image showed Earth as a point of light, less than a pixel wide, suspended in a scattered ray of sunlight, almost invisible against the surrounding black. 6 billion kilometers, less than 1,000th of a light year. The first step on a staircase we have now climbed together from here to the observable boundary of the cosmos. And from that first step, that trivial, cosmically negligible distance, Earth was already gone. Sagan wrote about that image with the full weight of what it represents. Everything you have ever known, everyone you have ever loved, every war ever fought, every civilization ever built, every kindness ever extended, every cruelty ever committed, every discovery ever made, all of it on that pale point of light, barely brighter than the surrounding stars. Here is what we have learned since that photograph was taken. Every atom in your body was forged in the core of a star. The iron in your blood was built by nuclear fusion in a stellar interior and released into space by a supernova. The carbon in your cells was assembled in the dying breath of a star several times more massive than the Sun. The hydrogen in every molecule of water in your body has existed since the first 3 minutes after the Big Bang. Older than any planet, older than any galaxy, older than the cosmic web itself. You are not made of Earth. You are made of the universe, temporarily assembled into something that can ask questions about it. The universe spent 380,000 years as a featureless glowing plasma, then roughly 200 million years in total darkness. Then, it ignited the first stars. Enormous, short-lived, violent. And those stars seeded the void with the first heavy elements. Then, across billions of years, gravity gathered those elements into galaxies, and galaxies into clusters, and clusters into the vast filaments of the web. And somewhere on a thread of that web, a star formed with a planet at the right distance, and on that planet chemistry crossed a threshold it had never crossed before. And eventually, that chemistry produced something capable of measuring 93 billion light-years from a rock, 12,742 kilometers wide. The Boötes void is 330 million light-years of near emptiness. It has never known it is empty. The cosmic web spans the entire observable universe and has never seen itself. The Hubble tension is a 5 sigma crisis at the heart of cosmology, and it only matters because something is here to notice. Dark matter shapes the architecture of everything we observe, and has done so since before any star existed, in complete indifference to whether anything would ever be there to observe it. The universe is not large in a way that makes you small. It is large in a way that makes your existence extraordinary. It built the conditions for you across 13.8 billion years of physics, not deliberately, not with any intent, but through the patient operation of forces that did not know they were building toward anything at all. And what they built, without knowing it, was something that could look back at the process and understand it. The universe has been running for 13.8 billion years. For most of that time, nothing knew it was running. The laws operated in silence. The stars burned and died unwatched. The web grew in the dark. Then, on one pale point of light, in one unremarkable spiral arm of one ordinary galaxy, something happened that had never happened before anywhere in the observable universe, as far as we know. The universe became aware of itself, not in any mystical sense. In the most literal, physical, observable sense, matter organized itself into a configuration that could turn outward, look at the rest of matter, and understand what it was seeing. That configuration is fragile and temporary. It will not last. In cosmological terms, it has already lasted almost no time at all. But while it lasts, it does something that nothing else in the observable universe appears to do. It wonders. That is what the size of the universe actually is, in the only unit of measurement that reaches the thing itself. It is the distance between nothing knowing it exists and something knowing it does. And that distance, measured not in light years, but in the improbability of the journey from hydrogen to here, is the largest thing in the cosmos.